So for this video, our lesson would be nodal analysis. So nodal analysis method was used in solving circuits having multiple voltage sources because simple Ohm's law fails to solve or somehow unable to solve these kind of complex circuits because they are dealing with multiple voltage sources or current sources. So nodal analysis was introduced. So in solving or in using the nodal analysis method in solving circuits, there are almost 4 steps to take. First step is to identify the nodes. Next step is to assign the reference node or the datum, which is actually n-1 because uh, the the nodes that will be used in solving the circuit will be only subtracted by one nodal voltages because one node will be used as a datum or a reference node. And third step is to apply Kirchhoff's current law in each nodes so that we can solve for the voltage at the nodes. And lastly is to solve for the nodal voltages using the simultaneous equations. Okay, so let's have our first example. So for our first example, using this circuit, okay, we need to find currents I1 and I2 using nodal analysis. So to do so, first step is to identify the nodes in the circuit. So actually there are 3 nodes in the circuit. This is node 1, this is node 2, and this is the common node which is node 3. Okay, so for the second step, we need to assign a datum or a reference point which will be our ground. So let's say the datum would be node 3. And in order to solve this circuit, we need to assign the nodal voltages. So to do this, um, what is the reason why we are assigning a datum or a reference point? So because in every circuit, for us to measure a voltage in every node, especially in this kind of circuit we're in, it is quite complex. We need to have a reference point. So because how can we define the the magnitude of the voltage at a certain node if we doesn't have a common reference point in the circuit. So to do so, let's assign nodal voltages. This is V1, okay, common node, and this is V2, common node again, positive, negative, positive, negative. And as you can see, uh, there are 5 currents that are present in the circuit. So this would be the IA. Let's denote this as IA. This is I1. This is IB. This is IC. Okay. IC, and this is IT. 1, 2, 3, 4, 5. 5 currents are present in the circuit. So as you can see, and if we apply KCL at node 1, KCL at node 1, this would be 24 volts, 24 volts, because this is IA entering, and IB and I1 are the current that are leaving the node 1. So IA would be positive, IA would be positive, then minus V1 because V1 is a much lower potential, and the resistance 10 ohms. It is a basic KCL because as you can see, this equation right here is equals to IA, right? And let's proceed. IB is leaving the node 1, so this is negative. What is IB? That is V1 exiting at node voltage V2, but V2 is actually connected here, okay? So that is V1 minus V2 over the resistance between them, which is 20 ohms. And again, I1 is leaving the junction or the node 1, that is again negative. V1 minus, this is 0 volts right here because this is ground, okay? 0 over 40 ohms, which is equals to 0. So if you look closely, uh, the essence of a datum is for I1, for this current IA, it must be a closed path because uh, this is 24 volts. This is V1 right there. And again, it closes to the negative side of a 24 volt voltage source and the resistance, and it was divided by the resistance between them, which is 10 ohms. That's how you get current IA. And as you can see, this is actually a closed path, as well as the current path in IB, that is from V1. Let's try another color. That is V1 again. V1, it passed through the resistor, and again V2, and again it is a closed path again, as well as the nodal voltage V2. So as you can see from V2, it passed the voltmeter V2, it traveled through these two resistors and then it closes again. Now that is the essence of a datum. Again, as a reference point to measure the voltage, the potential difference on the nodes, and to have a closed path so that our equations will be compatible, okay? And let's continue solving. Let's multiply both sides by 40 ohms times 20 ohms times 10 ohms, and let's divide it by 100, okay? So in here, at this point, this will just only be 8 times 24 minus V1. This will be negative 4 V1 minus V2. This will be negative 2 times V1, okay, is equals to 0. And finally, when we solve this algebraically, our the much more simplified equation will be 14V1 4V2 is equals to 192. And let's transpose V2 on the right hand side, and let's solve for V1. Therefore V1 is equals to 192 plus 4V2 divided by 14. That is the equation number 1. This equation is actually applied at node 1, therefore this we call this, rather we denote this as KCL at node 1, okay? So next step is to solve for the nodal voltage at node 2. So let's erase this. Next step is to apply KCL at node 2. So again, what are the current that are entering in the junction or in the node? That is IP 5 amps, and ID is the current that is leaving the node. Therefore, let's solve for that. Let's solve for this. Okay, so IB, what is IB? That is nothing but V1 minus V2 divided by 20 ohms. Again positive because 5 amps is entering, 5 amps, and ID is leaving. What is ID? That is nothing but negative V2, negative V2 minus 0 volts because it is going to this direction, which is the datum or the reference, which is 0 volts, and divided by the total resistance on that path, that is nothing but 50. And let's equate it to 0. Okay, so again, to solve this, we multiply 20 times 50, that is 100 right there. So for the to simplify this, let's divide it by 100. Okay, rather 10 only, because that would be a very small value. So again, 20 cancels out. We will left with 5, that is 5v1 minus 5v2 plus 5 times 5 times 2, that is 100 times 5, that will be 500. And again, at this point, this cancels out. That is nothing but 20 over 10, that is 2, 2v2, which is equal to 0. Therefore, the next equation will be 5v1, okay, minus 7v2 is equals to 500. This is positive right here, therefore this is negative 500. And let's solve v1. We equate v1, it is nothing but negative 500 plus 7 v2 divided by 5. Let's mark this as equation number 2. Okay, so let's solve for the simultaneous equation, which is the last step in order for us to solve the nodal voltages. So let's erase all of this, and let's equate equation 1 and equation 2 so that we can solve for v2. Okay, that is nothing but 192 plus 4 v2 over 14 is equals to negative 500 plus 7 v2 over 5. We cross multiply. Okay, we cross multiply, we get 960 plus 20 v2 is equals to negative 7000 plus 98 v2. Therefore, v2 is equals to 102.051 volts. Okay, and using equation 1, v1 is equals to 192 plus 4 times 102.051 divided by the 14 is equals to 42.872 volts. Okay, that is v1. This is v2. And the problem is finding I1 and I2, but it is very obvious in this circuit that I1 is equals to V1 minus 0 volts divided by the total resistance in the branch, which is 40 ohms. Therefore, that is equals to V1. What is V1? 42.872 volts minus 0 divided by 40 ohms. That is equals to 1.072 amps. Okay, and to find I2, that is nothing but okay, that is V2 minus 0 volts divided by the total resistance in that loop, that is 30 plus 20, which is 50. Therefore, that is 102.051 minus 0 divided by 50 ohms, that is equals to 2.041 amps. There you have it. That is the final answer, and I hope you enjoy and you learn how to do the nodal analysis method. Uh, it's quite uh, it's quite useful when solving this kind of circuits wherein you have multiple uh, current and voltage sources. Okay, so that's all. Thank you.
Rufus boy, let me love boy, what you know. Rufus boy, let me love boy, what you know.